Good day, everyone. We are from Group 7 would like to present on production of ethylene glycol. Ethylene glycol is a chemical compound with the molecular formula C2H6O2. Diethylene glycol and triethylene glycol are oligomers of monoethylene glycol. It is a colorless, odorless, and sweet-tasting liquid at room temperature. Ethylene glycol is highly soluble in water and miscible with many organic solvents, making it a versatile compound with various applications. The usage of ethylene glycol are as follows. Firstly, ethylene glycol used in textile industry to make polyester fibers. Next, it is used in the production of plastic bottles, packaging films, and synthetic fibers. It is also used as anti-freeze solution for automotive and industrial sector. Lastly, it is used as a solvent in personal care products. Now, we will discuss more on economic issues. This is the supply and demand graph. From this graph, we can see the trend keep increasing from year 2018 until 2033. The compound annual growth rate CAGR of ethylene glycol expected to achieve 5.3%. These factors indicate a positive trajectory for the market in terms of both supply and demand. In the year 2020, North American nation exported more than 2.2 million metric tons of the compound, valued at 93.2 million US dollar. Saudi Arabia ranks second in ethylene glycol exports, with a total export of approximately 907.2 million US dollars. According to the data monitoring of eChemi, as of June 2nd, 2023, the average price of ethylene glycol in the domestic market was 500 US dollar, which is equivalent to RN 2,325.25 ringgit Malaysia per ton. These are the calculation for our plant capacity. The plant capacity was calculated based on the supply and demand from the graph and also considering maintenance days in the plant. Also, our plant is planning to cater 3.5% of the world's demand for ethylene glycol. The production rate of ethylene glycol estimated to be 182,110 kg per hour.
Moving on to the process selection. Ethylene glycol can be produced through several approaches. One method is the ethylene carbonate process, where the ethylene oxide reacts with the water to form glycol. Another approach is the union carbide syngas process, which involves generating syngas and then reacting it with the oxygen using a silver-based catalyst to produce the ethylene oxide. The ethylene oxide is subsequently hydrolyzed with water and a catalyst to obtain the ethylene glycol. The halcon acetocytolactin process involves the reaction of ethylene with acetic acid to produce ethylene glycol acetate, which is then hydrolyzed to obtain ethylene glycol. Additionally, the Thein oxychlorination process utilizes the reaction of ethylene with chlorine and oxygen to form ethylene dichloride, which is hydrolyzed to produce ethylene glycol. Among these approaches, the hydrolysis of ethylene oxide is widely used and considered the most common method for producing ethylene glycol. This process involves the reaction of ethylene glycol with water under suitable conditions such as the presence of an acid catalyst. The hydrolysis of ethylene glycol results in the formation of ethylene oxide. The advantages of this method include its simplicity, reliability, and the ability to be used in the plant that manufacture ethylene oxide and glycol together. The hydrolysis routes offer a proven, versatile, and efficient pathway for the ethylene oxide conversion to ethylene glycol in industrial applications. Moving on to the process design 1. Raw material selection. Ethylene oxide is the primary raw material and water also considered as the raw material of this process. For the reaction condition, it is an exothermic reaction and then the reaction conversion is 90%, the selectivity is 99%, the yield is 98%, and then it is a silver-based catalyst is used, and then for the stoichiometric reaction equation is shown in the slide where it involves ethylene oxide will react with the water with the aid of silver-based catalyst to produce the ethylene glycol. For the product and byproduct identification, ethylene glycol is produced as the main product and diethylene glycol is produced as the byproduct. When designing a hydrolysis process for ethylene glycol production, several common design constraints need to be considered. Firstly, reaction kinetics plays a crucial role, and the design should aim to achieve desired conversion rates by selecting suitable reaction conditions such as temperature, pressure, and residence time. Safety considerations are also vital as the process involves handling hazardous materials. Design must incorporate proper containment system safety measures and process control to minimize the risk and ensure worker and environmental safety. The selection of an appropriate catalyst is another important design constraint. The chosen catalyst should exhibit a high activity, selectivity, and stability while also considering the factors like availability, cost, and potential site reactions. Efficient separation and purification steps are necessary to achieve the desired purity of ethylene glycol and minimize the generation of waste streams. These steps should effectively remove impurities and byproducts while minimizing losses and maximizing the product yield. Environmental impact is a critical consideration, and the design should aim to minimize the re- release of the environmental impact is a critical consideration, and then the design should aim to minimize the release of pollutants, optimize resource usage, and implement effective waste management strategies. These include adopting environmentally friendly practices and technologies to reduce the overall environmental footprint of the process. By addressing these design constraints, the hydrolysis process for ethylene glycol production can be optimized to achieve the efficient safe, environmentally friendly, and economically viable operations. Moving on to the process design 2, the shown figure is the input-output structure where it involves the reaction of ethylene oxide and water as a raw material, and then the product and byproduct is ethylene glycol and diethylene glycol. The component firstly is ethylene glycol. The boiling point is 197, so it is considered as the light component. So the destination is primary product. Next, the diethylene glycol is considered as a heavy component, and because the boiling point is 245 degrees Celsius, and then the destination is it is as a byproduct. Next is process design level 3. The figure shows the block diagram design for the production of ethylene glycol, where it shows the number of reactors and separation system involved along with the input, output, and recycle at each system. Moving on to the process design level 4. This is the PFD of our plant. The production of ethylene glycol begins with the reaction of ethylene oxide and water in a glycol reactor. This reactor operating at a temperature of 105 degrees Celsius and a pressure of 1.5 MPa employs a catalytic plug flow design with a liquid phase and an ionate phase containing the catalyst. The preheater unit ensures that the feed mixture of the ethylene oxide and recycled water reaches the desired reaction temperature. The reactor's efficient operation and optimal reaction kinetics are maintained by the adequate heating in the preheater. The effluent from the reactor then undergoes evaporation in a multiple effect evaporator utilizing steam heat to remove excess water. The evaporator operates at the 50 degrees Celsius and 1 bar pressure, employing a series of vessels operating at progressively lower pressure. The evaporated water is recovered as a condensate and recycled, while the water-free glycol solution continues to drying unit. In the drying unit, a vacuum-based drying unit column removes most of the remaining water from the glycol solution, with the water vapor being directed to the monoethylene glycol (MEG) recovery unit. The dried glycol solution is then sent to a distillation column where the ethylene glycol is separated from the heavier glycol, which is the diethylene glycol. The purified ethylene glycol is obtained as the desired product, while the bottoms of the column undergo further processing in a splitter column to remove the remaining monoethylene glycol and separate the heavier glycol for byproduct storage.
Now, we will discuss more on environmental and safety issues. Safety is top priority in plants. Strict safety precautions should be followed. When handling compounds like ethylene oxide, ethylene glycol, and diethylene glycol, we avoid open flames, use closed systems, proper ventilation, and non-sparking tools. Efficient material handling and proper storage practices are essential in manufacturing. By following appropriate guidelines, we can prevent accidents and ensure the safety of personnel. For example, when handling materials like ethylene oxide, we can use safety gloves and shoes and employ explosion proof equipment. The production of ethylene glycol through the hydrolysis of ethylene oxide result in the generation of different type of waste materials. These include wastewater residual, ethylene oxide that did not undergo complete reaction, unreacted catalyst, and steam gas. The wastewater generated when water is used as a reactant and solvent in the hydrolysis process. It helps facilitate the reaction between ethylene oxide and water molecules. The water used in the process becomes part of the wastewater stream. Also, regular cleaning and maintenance activities in the plant, such as equipment rinsing or flushing, can contribute to wastewater generation. Incomplete conversion of ethylene oxide to ethylene glycol can occur during the hydrolysis process, leading to the presence of unreacted ethylene oxide in the reaction mixture. This unreacted ethylene oxide needs to be separated and purified. Next, the unreacted AG catalyst may contain trace amount of contaminants, metals, or other chemicals that require proper handling and disposal to prevent environmental contamination. Lastly, the steam gas waste generated in formation of ethylene glycol coming from dryer, which will vaporize the water from ethylene glycol. These waste have their own waste management system. Wastewater should be purified before recycling back to the process. Next, neutralize unreacted ethylene oxide by using calcium hydroxide. This is an additional purification step to remove impurities to avoid low quality of desired product because concentration of ethylene oxide can affect final product purity. Furthermore, the unreacted catalyst collected separately in designated containers and sent to quality alarm. We do not prefer to recycle back the catalyst because regeneration of catalyst requires extensive processes which can increase the cost. Lastly, the steam gas will be recycled back to the process by using appropriate equipments. Presented here are the applicable acts and regulations pertinent to our plant operations, such as Environmental Quality Act 1974, Occupational Safety and Health Act 1994, and Factory and Machinery Act 1967. Production of ethylene glycol can be linked indirectly to a few SDGs, such as SDG 9 and 12. SDG 9 is followed where ethylene glycol production involves industrial processes and infrastructure development. Implementing resource efficient and sustainable practices within the production process aligns with the objective of promoting sustainable industrialization and innovation. Ethylene glycol production can contribute to SDG 12 by adopting resource efficient practices, reducing waste generation, and promoting the circular economy approach. In this production, this SDG implemented by recycled water usage in our plant. So these are the conclusion. Ethylene glycol is a versatile compound used in various industries, including textile, plastics, and automotive applications. The global demand for ethylene glycol is increasing with a projected healthy growth rate. The design plan is expected to meet 3.5% of the global ethylene glycol demand with a capacity of 1,595,283.6 tons per year. The production process involves hydrolysis of ethylene oxide with a high conversion rate of 90% and a purity of 99% for ethylene glycol. Safety measures are implemented adhering to the legal requirements and identifying potential hazards associated with chemicals used in the production process. Waste generated such as steam gas, catalyst, wastewater, and unreacted ethylene oxide are managed through treatment, recycling, and proper disposal methods. The design plan is cost efficient, environmental friendly, and economically viable due to its single step reaction and waste management strategies. These are the references we use in our project work. Thank you from us.